Yeah, can you see my screen?
Yes, sir.
Yes.
Yes, sir.
All right, so you can see my screen. All right, so let's start the session. So this time we are back with the new webinar topic that we had long pending. So since the bridge design has to start from the bottom of the what you can say, the structure has to start from the foundation. So we decided that we'll have a topic on the design of shallow foundations for bridges. And in particular, I will be dealing with the metro viaducts. All right. So is my volume too loud, Navi, or is it okay?
He is perfect, sir.
All right. All right. Okay. So just to give you a small introduction about myself, adding up to what Naveen had said. So a few years back when I was in Bombay, I was a part of the design team that was designing Bombay Metro and Pune Metro. So I was a part of the DDC, the detailed design consultant. And over there, what we were doing was rigorously carrying out design and analysis activities. So over there, my interest into bridge and bridge designing shot up, and I thought of having something of a platform wherein I could reimagine the different aspects of bridge design and present it to the people who are willing to learn more about it. So that was the basis of why I started Bridgehawk. And now, gradually or rapidly, you can say, we are growing up into something, and people are noticing, and we have been receiving a lot of support from all around the world. And this Bridgehawk is a platform wherein we reimagine the concepts of structural engineering and bridge design so that it can be well presented and well understood by students, by professionals, by everyone. So this is just my small initiative towards sharing the knowledge that I have gained over the years. So if any one of you wants to contribute anything towards the platform, you're more than welcome. We are more than happy to have you have any sort of contribution from your side. Contribution in the sense of contributing technically, contributing it by your skills, by your creativity, anything. So we are open to displaying or showcasing your work on our platform. So this is a brief introduction about Bridgehawk. So we'll start with our today's topic. So starting with the basic question, what are these bridge foundations? So bridge foundation, the foundation is the base of a bridge that transmits the loads from the piers, abutments, and the wings to the supporting strata. So foundations usually are categorized into two different types. One is a shallow foundation and another is a deep foundation. For the sake of the webinar that we are going to have, we will only be dealing with open foundations. If in case you want to, you have an interest in knowing about pile foundations, do let me know, do let Rajakumar know, so that we will accordingly plan a session on pile foundations. So for the sake of this presentation, we'll be delving into the open foundation topic. So in the last webinar, I had shown you this sketch, and there would be some references to the last webinar that I had conducted. So basically, the bridge is parcellated into three different parts. The top one, as you can see in the sketch, is the superstructure. The one in the between is the substructure, and the foundation is that portion of the viaduct which lies below the ground. So basically, the substructure is comprising of the pier cap, seismic arrestor, the pedestals, the bearings, and if at all there's any other component involved. The substructure is typically your entire girder. So over here in the sketch, that is a multi-cell box girder. So that about sums it all what superstructure actually is. So the foundation, the footing, the shallow foundation is a part of that foundation, that the three parts we have made of a bridge. So moving on, shallow foundation. So what is a shallow foundation? So it is also known as a spread footing or an isolated footing or a single column footing. So it is considered as such when the width of the entire foundation is greater than its total depth. So implying that the depth is not exceeding its width. Only in that case, we'll call it as a shallow foundation. Around the world, this is the most economical and most common type of foundation that is used for bridges. Even for very heavy station piers, you'll find that we have been using shallow foundations. Even for Pune Metro, many of the station piers, they are designed on the shallow foundations. Okay, so this type of footing is used when the structural load is relatively low, columns are widely spaced, and soil bearing capacity is adequate at the shallow depth. So just to understand, because we'll be delving into what are the different types of loads, what are the category of loads that we're going to deal. So it is important to know what are the different components that comprise an overall viaduct of a bridge. Okay, so this is just a simple way of indicating what is what. So starting from the bottom, I've indicated that as a pile foundation. So it is a pile, there's a pile cap, there are crash barriers, there are piers, pier cap, bearing, the seismic arrestor, box girder, rail pedestals, and crash parapet. In the longitudinal phase, I've indicated that there's a right-hand side span, and a left-hand side span. So we'll be talking more about what is it exactly. Most of you have already at least seen a metro viaduct anywhere that you've gone. So it would be very easy for you to relate to something like this. Okay. Over here, what you see is like 3 spans. All of them are simply supported spans, and they are upon box girders. This is a model I made for one of my videos on Bridgehawk, the YouTube channel. So if you see, for the sake of this webinar, we'll be delving upon the PRP 177. So basically, this is a span arrangement. By span arrangement, what I'm trying to imply is that when I'm looking at P177, there is a span to the left of it, and there's a span to the right of it. And over here, there are 2 tracks. On one track, there's a train going on, and there's another track that is just besides it. When it is implied that there's a span on either side, we have to know the different details of the span. The details are implied over here. Okay, the carriageway details. The portion over there that you saw, it is a carriageway. So before beginning my analysis or my judgment of what sort of design I need to make for the foundation, it is very imperative to know the different types of loads that my foundation is going to experience. As along with it, it is important to know the lever arm that different forces are going to be multiplied with in order to create a certain moment. So this is a table which will be required when you start the design process. So when you're gathering the design data, the first thing that you need to know is the carriageway detail. In the table that you see, the first row is span. It is indicating the LHS span and the RHS span. The unit is in meters. So on the left-hand side of this pier, P177, on this side, I'm indicating that my span is 35 meters. And on my right-hand side, the span is 30 meters. So over here, what we'll have a certain sort of an unbalanced longitudinal movement. And the loads from the left-hand side span, the dead loads basically, will be more than the loads from the right-hand side span. So there will be, there would be a residual longitudinal movement. I'll be telling you about what is a longitudinal movement in a short while. So that is my first understanding of the span, that there is an unequal span. Second of all, coming to the second row, it is indicating what is the type of the girder that is used in the span. So in this case, we've got a post-tension box girder on either side of pier 177. It might be the case that you have a different sort of a girder on either sides. It also can be possible that you have a concrete girder on the left side and you've got a steel girder on the right side. So it completely depends upon the designer's understanding, not the understanding, but the preference of how he wants to encounter this challenge. So it is upon his assessment. As long as he can prove it to be safe, he can design it. So now the width of box girder is 9 meters. The depth of the box at the centroid is 2.5. So this is basically implying the height from the top of the girder to the centroid is 2.5 meters. The center to center distance of the tracks is 4.5 meters. The cross slope is 0.025%. Why do we need a cross slope? Cross slope is to be provided in the section of the girder. Cross slope is basically to drain off any water that is coming upon the girder. This numbers, okay. So the bearings, number of bearings that this girder is resting upon is 2 on either sides. The width of this bearings is 3 meters, which is indicative of the distance. Bearing center to center from the pier center is 1 meter. I'll show you what this means actually in the later slides. And over here, I've mentioned radius of curvature is none. So what this is implying is that over here you see these are straight spans. There is no curvature included. We don't have any radius of curvature, because having a radius of curvature exponentiates our challenges. Because if you had a curvature over here, in order to have, like if you just had a curvature, the level of centrifugal force that you'll have, that will be huge. And certain other forces would exponentially increase. So for the sake of the discussion on this webinar, I've taken a straight span on either sides. Okay, so moving on. All right. So the design data, what you need to understand is you need to know the location details. What is the pier number? What is the chainage? Chainage is basically implying the distance from the pier from an imaginary straight line. The pier height, what is the height of this pier? All different design levels, which I'll show you in the later slides. The pier cap details, what sort of pier cap is it? Is it a flat pier cap? Is it a hammerhead? Is it a post-tension pier cap? Or is it an RCC pier cap? RTL to floor level, I'll show you what this is. This is rail top level to the floor level. So what is the extent of the heights that we're dealing with? And the seismic coefficient. Like for example, this bridge can be in an earthquake active zone, or it can be in a zone where the seismic coefficient is not very deterministic. Second, we just read about the carriageway details, the material details. There has to be a material table, which I'll be showing you. Has to be a span arrangement. What is the number of tracks? What is the distance? What is the type of footing? The span on either sides. The sectional data. What is the type of the section for the pier? What section is it for the pier cap? What is the section for the box girder or the eye girder or whatever girder that you have? All right. So basically, many of these things are specified in the DBR that is submitted to us by the client. So in the case of metro projects, which are very prestigious projects, the DBR is, the DBR has to be provided from the government, the client. Okay, so the client is basically specifying what he's expecting of you, of the design. So in this design basis report, he has to specify every single thing that he has anticipated in the process of having his design project actuated. So before starting any project, a well-defined design basis or a criterion, in addition to a well-defined scope of work, has to be set forth by the client. A DBR document is the criteria which, or the rationale, which has the principles, the assumptions, and the constraints used for the detailed engineering and the final design product. It is essentially a set of conditions, requirements, needs, the needs of the project, the performance, maybe timelines also, in legal and codal requirements, obligations, etc. So everything that needs to be known before you start the project or before you anticipate the end of the project, it has to be mentioned in the DBR. With the name, it has to also, with the name, it is implying it is a design basis report. Sorry. So it has to include all the different factors which the structural engineer might be requiring in order to complete his design safely and sufficiently, in order to satisfy the client. All right, whatever data he has to require, it has to be mentioned in the design basis report. So basically, this includes the concrete and steel grades, type of girders, construction methodology, what type of launcher you are going to use, what type of this you are going to use, which construction methodology, what type of shuttering you're trying to, you should be using, section geometry, test required, load cases, combinations, which code you have to follow, different, etc.